Okay, as I mentioned, this event was really important to me because seeing and hearing the event at the same time meant we could do something really incredible that we hadn't been able to do before. And this was something I took part in. We could see what happens in a race between the gravitational waves and the light. So what we want to do here is effectively measure the speed at which gravitational waves travel. And I call it a race because these things are going to set off at the same time from our binary neutron star merger. They're going to travel the same distance to the Earth, so we see who gets there first. Now, we have a little demo for this as well. Okay, and you'll notice, folks, that I'm putting on ear defenders and safety goggles. You'll be fine, but please do cover your ears. This is going to be loud, okay? I'll give you a signal before we get going. But once I give you the signal, please do cover your ears. I'm now not going to be able to hear anything. Yes, I think that's a wise. So there's that, and I need the stop clock as well. Okay, and what we've got here is we're going to have our neutron star merger. And at the far end there, we've got two little flags, one that's going to pop up to represent the gravitational waves arriving, and one that's going to pop up to represent the light arriving. And it's gravitational waves in blue, it's light in yellow. Okay, and I'm also going to attempt to time these things here. So, just set that going. Okay, folks, please cover your ears. Off they go. Oh, I wish I could do that in every talk I give. Okay. So, what happened? We had our neutron star merger, our two signals set off towards the Earth. Now, they actually arrived pretty close together, but if you were watching closely, the gravitational waves arrived slightly quicker. I can't say my timing accuracy was brilliant, but I got them here as about 2 seconds earlier. Okay, at least that's what I got. Okay, so if that happens, if one event arrives earlier than the other, get the wrong one of those, that means it must have been traveling faster, right? So we can use the information about which we saw first to say which one's the fastest. So here comes the second equation of the talk. And again, I hope it's something that's familiar to a lot of people. If you did high school physics, you might remember that you can measure a speed as taking the distance traveled divided by the time taken to travel that distance. Now, we don't quite use this formula in astronomy. I'll be totally honest, it's a little bit more complicated, the actual calculation we do. But basically, it's a poshed up version of this. Okay, so what have we got? We need to know the distance to our binary neutron star. That's 40 megaparsecs. What megaparsec? What's that? That is another unit that astronomers define to try and make the mind-blowing numbers we work with every day manageable. So actually, a megaparsec in meters is about 30,000 meters. Okay, but when we define these units, we can just say it's 40 megaparsecs, and it sounds like it's a kind of, just around the corner. If you prefer thinking of it this way, that's about the length of the UK, 1,000 kilometers, 600 miles if you're imperial, multiplied by the number of grains of sand on the planet. Yikes. Okay, that's the distance. And the time it takes, well, we know the speed of light already, so we know that part of the problem. We know it would take light 130 million years to travel that distance. What we don't know is the speed of gravitational waves. And in the real experiment, what we found is that the gravitational waves arrive first. They arrive about 2 seconds before the light does. Okay, so their travel time, 130 million years minus 2 seconds. Okay, so what's the speed going to be? Well, as I said, we do know from other experiments on Earth that the speed of light in vacuum is 299,792,458 meters per second, to be precise. The speed of gravitational waves comes out as 299,792,457.99999 meters a second. So they're basically the same. If we look at the last 2 digits, we've got 58 and we've got 57.9999999. Okay, in fact, it turns out that the greatest difference in speed that is allowed by the data is that percent. Again, I can't even pronounce that. Okay, it's tiny. And probably, that tiny difference is just due to the errors in our experiments. Right? When we do scientific experiments, we can never do them perfectly. There's always some kind of small systematic error. So it seems that gravitational waves travel at, or at least very, 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 very close to the speed of light. And that's actually a win for Einstein, because that's exactly what he predicted. His general theory of relativity says that gravitational waves should travel at the speed of light. Okay, so Einstein wins. Now you might say, why do we bother doing this? You know, we know Einstein's theory is correct. You know, why did you need to go and check that gravitational waves travel at the speed of light? Actually, that's slightly oversimplifying the situation. For me as a cosmologist, if Einstein's theory is fully correct, that means there's something else very wrong with our current understanding of the universe. So we take Einstein's theory that seems to work really well every time we test it, and we apply it to the universe as a whole. And we can ask it the question, how fast is the universe expanding? Okay, and Einstein's theory says it should be, expanding at a moderate rate or a constant rate. And actually what we find when we use other data to measure the speed of expansion of the universe is that we find it's speeding up. It is actually accelerating. And that's completely, almost the opposite of what Einstein's theory predicts. So there's a problem here. There's something going wrong. Either Einstein's theory is incorrect and we can't apply it to the universe as a whole, which means there's still more we need to learn about gravity, or we have something else in our universe. Okay, and we don't know what this something else is, so as a placeholder for our ignorance, we give it a name that makes us feel better about it, and we call it dark energy. But if this dark energy, this strange new substance that causes the universe to accelerate, if it exists, it has to make up 70% of the universe. Okay, so this is just a simulation here showing galaxies and dark matter in the universe, but 70% of that has to be made of something else. So if I've given you the impression at all this evening that cosmology and gravity is kind of sewn up and done and dusted, please forgive me. That is certainly not the case. There are major, major questions that we are still trying to answer. Okay, folks, I'm nearly done for this evening. Let me just wrap up by telling you about the gravitational wave detections that are about to start. So these detectors that I showed you images of here, they've actually been offline for about 3 years. And that was initially due to the pandemic. We had to take them offline for the safety of the people working there. And then they were having a lot of engineering work done, as you can see, to make them more sensitive. They were having upgrades. That's basically all done now. And our next observing run is due to start in 5 days' time. Okay, so this talk is super well timed. It starts on the 24th of May, which is next Wednesday. Now, actually, as I said at the start of the talk, things have started happening already. Right now, we are in engineering mode, which means we're not fully calibrated, we're not supposed to be seeing anything. But if something happens, and the engineers are there testing the detectors, but they're online, we can't help but detect it. Okay, so we have our first candidate event. Maybe it'll be confirmed, we have to see yet. But nevertheless, 5 days' time, we switch on. So doubtless we will see more black holes, more neutron stars, and hopefully a few more unexpected discoveries along the way too. If you would like to follow along, you can do. There is an app on your phone called, well, it's not on your phone right now, sorry. There is an app for your phone, if you wish it to be on your phone, called Gravitational Wave Events. What this does is it plugs into a set of alerts that are sent out worldwide if we find something interesting. So you can get a notification on your phone. If you choose the settings correctly, it will actually play you one of these gravitational wave chirps. So your phone can go whoop when you've got a gravitational wave detection. I mean, it's pretty cool. Alternatively, of course, if you don't want your phone going whoop all the time, you can follow the LIGO detectors on Twitter. Okay, I will leave it there, folks. Thank you so much for listening, and I look forward to some questions.